This video is part of the lecture for multivariable calculus, and I'm gonna talk about critical points, basically maximum and minimum value. So let me start by reviewing single variable case. If we have a single variable function like this, f of x equals to y, then when we say let f be a function from the domain, which is basically, since we have just one variable, it's a subset of R, to R be a function, then a point A is a global, sometimes we call it absolute maximum, if the value of the function at the point A is greater than or equal to the value of the function of all other points in the domain D. A is a local maximum if the value of the function at A is greater than the value of the function at all the points that are in N, where N is a neighborhood of A. So for example, if this is the point A, some interval that contains A. D here is the domain. So you see the difference between these two. For a point to be the global maximum, we need the value of the function at A to be greater than all the other points. But when we say that a point A is local maximum, it means that at a small neighborhood that contains A, the value of the function at A is greater than the value of the function at other points. As a small note, we can define global or local minimum basically the same, but we need to have the value of the function at A to be less than or equal to the value of the function at the points X. For global minimum, we need f of A to be greater than f of x for all the x in the domain. For local mean, the value of the function at A is less than f of x for all the x's that are in the neighborhood of the point A. Now, how about the two variable case when we have a function of two variable like this? Then we say let f be a function from D, where D is a subset of R2 and it goes to R3, be a function, and let's pick a point A and B in the domain. Then we say the point A and B is global maximum if the value of the function at A and B is greater than the value of the function for all other points in the domain, and the point A is local maximum if the value of the function at the point A and B is greater than the value of the function at all other points that are in the neighborhood of A and B. And the neighborhood here would be, so I have this, and the neighborhood would be just a disk like this. So this is N. It's a disk. It's a disk contained containing x and y. I'm sorry, containing a and b. Containing a and b. Yeah, so it would be the neighborhood, just one neighborhood at the point A and B. Okay. So that's definition of global or local maximum or minimum for a function of two variables. And as you see, the definitions are kind of similar. Okay, now let's talk about the critical points, and I'm gonna go over the single variable function first. If we have a single variable function like this, y equals to f of x, we define the critical points by saying that derivative at the point is equal to 0, or we say that the derivative at the point does not exist. Does not exist. So when derivative equals to 0 at the point, we might get a minimum like this. As you see, the tangent line is horizontal. It means that derivative is 0. We can get a minimum, we can get a local maximum, or we can get neither. In all these three cases, derivative is 0 because the tangent line is horizontal, but we might get a minimum, maximum, or neither. And when derivative does not exist at the point, we might get a situation like this. And as you see, derivative does not exist because the function is not even continuous. And on here we have a wedge, which means that the derivative at the point A does not exist. So how about the two variable case? So when we have a function of two variables like z equals to f of x and y, then when we want to define the critical points, we say the critical points are the points where the gradient of f at those points is equal to 0, which means what? Which means that the partial derivative at the point with respect to x is 0, and both of them, the partial derivative, or we can say that the partial derivative with respect to x does not exist, or partial derivative with respect to y at the point does not exist. So in the first case, both of them should be equal to 0 at the same time to make the gradient is 0 at the point, or in the second case, just one of them, if they don't exist, then we have a critical point. So let me give you just one small note, and is that at a local mean or max, the gradient of f is equal to 0 because derivative in all directions is 0. Let me move this line in here, because derivatives in all directions is 0, which means that the directional derivative of f in all of the directions at the point of local mean or max is 0. Okay, very good. Now you can compare the single variable case with the function of two variable when we define the critical points. Okay, let's look at one example. Find critical points of the function f of x and y equals to x squared minus 2xy plus 5y squared plus 2x minus 2y. Okay, to solve that, I'm gonna take partial derivative with respect to x first. So I get 2x minus, with respect to x, y would be constant, so minus 2y plus 2. So this one and that one would be 0. And then I get partial derivative with respect to y, which is negative 2x plus 10y minus 2. And since both of them are polynomials, which means that the derivative, the partial derivatives, they exist. So I just need to check when both of them at the same time are equal to 0, which means that I need to solve a system of equation, and I need to find x and y that satisfies both these two equations. Okay, so how do I do that? I just add them up. When I add them up, these two would be cancelled, so I get what? I get 8y equals to negative 2 plus 2 is 0. So based on that, y is equal to 0. I'm gonna plug in y equals to 0 into just one of these equations. So when y equals to 0, 2x is negative 2, meaning that x is equal to negative 1. So the x coordinate of the point is negative 1 and the y coordinate of the point is 0. So the only critical point here is negative 1 and 0. And so the value of the function at negative 1 and 0, just plug it into here. This is 0, this is 0, this is 0. Negative 1 is square minus 2, which is negative 1 actually. Negative 1. Okay, let me show you to the graph of this function. You see, this is the function z equals to x squared minus 2xy plus 5y squared plus 2x minus 2y. The function looks like this. It's a paraboloid, you see, and it does have only one point where the x is negative 1 and the y 0. As you see, this is this point that, as you see in the shape, that it's local minimum. But how about algebraically? How can we say that the point that we got as a critical point is local mean, local max, or neither saddle point? So we need a second derivative test that we are going to cover it in the next video.